Okay, sampling and sampling distributions. So some of this you may not have covered in your last stats class, the sampling part of it, but sampling distributions you certainly did. So a lot of this will again be review for most of you. So a parameter is a number used to describe a population. We already went over this. A statistic is a number calculated from a sample and is used to estimate the parameter. A sample is said to be biased when summary characteristics of the sample differ systematically from those of the population. And so we're going to recommend sampling at random to avoid bias. So a way to avoid bias is to make sure you're using random sampling. There are two main ways that we collect data. An observational study just merely observes cases and records variables of interest, but no treatments are applied by the investigator. An experiment is different. It's a study where treatments are applied. We perturb Mother Nature. The goal of an experiment is to make a statement regarding cause and effect, i.e., randomly allocating the treatments to subjects should indicate the treatment causes the change in the response. So experiments allow you to make a causal conclusion. In an observational study, it's much more difficult to make a causal conclusion. We can just say that we observed them happening together. The variables are associated, whatever. Now think about the Surgeon General's warning about how smoking causes lung cancer. Obviously, we didn't make experiments to determine that causal relationship. It would be unethical to assign people to smoke or not for their whole life. So we used observational studies, and what they do is they have to work a lot harder to make that causal statement. They bring in lots and lots of experts, have lots and lots of repeated observations of the same thing, and then they finally can make the conclusion that one thing causes the other. But in general, for you guys, an experiment can determine a causal relationship and an observational study can't. All right, let's do an example. In the Canadian National Breast Screening Study, researchers were exploring whether routine mammograms would reduce breast cancer rates in women. Women in the study were allocated to either the mammography screening group or the control group for 5 years. At the end of the study, researchers checked each woman for breast cancer and found no significant difference in the rates of breast cancer. Is this an observational study or experiment? Notice that we said women in the study were allocated to either the mammography group or the control group. That means that we applied treatments, so this is an experiment. How many treatment groups were there? Well, there was either mammography screening group or the control group, so there were 2 treatment groups. All right, another example. A marketing agency for dental practices was excited about the results of a study that proclaimed good oral hygiene could prevent HPV infection in the mouth. The study was conducted to research the effect of oral hygiene on oral HPV infection. In a nationally representative survey, people who reported that they had poor oral health had a 56% increase in the risk of HPV infection in the mouth and throat. In the analysis, researchers also accounted for subjects smoking and having oral sex. Is this an observational study or an experiment? This one is an observational study, and it's a special one called a survey. We'll talk about that in a minute. They didn't assign anybody to do anything different than they normally would, so it's an observational study. All right, so when the respondents in a sample provide their own data, we call this a survey. A sample survey is a special type of observational study. When a survey attempts to use the entire population as the sample, this is called a census. So now we have 3 ways to collect data: an experiment, an observational study, and a survey, which is a special type of observational study. What else should we consider? Well, we want to reduce both bias and variability in any study. These are 2 different things, 2 different types of offness that we want to be able to control. So we want to reduce bias and variability. So let's talk about some techniques. Randomization. Selecting individuals at random helps avoid bias. Randomization distributes different characteristics equally among all groups. Randomization helps ensure that on average, the sample looks like the population. Random sampling reduces bias. Remember that whenever I ask you about reducing bias, this does not have to do with sample size. A bad sampling scheme is bad whether it's for 10 observations or for 1 million. All right, sample size. Sample size matters and the population size doesn't. You need a large enough sample to be representative of the population. A larger sample reduces variability. So a way that you can reduce variability whenever I ask you, you should always tell me, get a bigger sample. All right, back to parameters and statistics. A parameter is a number that describes the population. We usually don't know the value of a parameter, but it's some fixed number that exists. We just can't see it. A statistic is a number that describes the sample. We do know the value of a statistic because we've observed the data and we can calculate the value of a statistic like a sample mean. However, it will change from sample to sample due to sampling variability. So let's practice an example. A recent Pew Research poll asked 790 adults with at least a bachelor's degree questions pertaining to certain behaviors that would have better prepared them to get the job they wanted. 300 of those polled wished they had studied harder during college. So let's identify the sample, the population, the statistic, and the parameter. So first of all, what's the sample? Well, the sample is everybody that they contacted to ask these questions. That's the 790 adults with at least a bachelor's. What would the population be? That's who they're trying to say something about. That's the larger group that the sample should have come from. So this is all adults with at least a bachelor's degree. All right, what about the statistic? Remember, the statistic is a number that's calculated on the sample. So the statistic here is 300 adults with at least a bachelor's who wish they had studied harder during college. That's just one example of a statistic. I could have changed that into percent of the sample that wish they had studied harder during college. What's the parameter? That would be all adults with at least a bachelor's who wish they had studied harder during college. So that statistic describes the sample, and the parameter describes the population. Okay, a simple random sample is the most basic type of random sampling scheme. A simple random sample of size n is one where every subgroup of n units in the population has the same chance of being chosen as any other subgroup. And one way to think about this is putting all the names into a hat and drawing out your sample, or putting an identifier of each unit on a ping pong ball, mix them up in a large bin, and then draw out the number of ping pong balls needed. So it's the most basic type of random sampling scheme. A simple random sample has the property that many of the common statistics, means, variances, and percents calculated from them are unbiased for the corresponding population parameter. That is, on average, the statistic will equal the parameter. If your statistics are biased, then you're going to be overestimating or underestimating that population parameter. If on average the statistic will be estimating equal to the parameter, then it's unbiased. If the statistic differs from the parameter on average, then it's said to be a biased estimate. All right, an issue we need to work around. We'd like to draw the sample from the population. However, we often don't have a list of the entire population. Think about trying to poll all U.S. adults. There's no way that you can get a list of all U.S. adults. So the sampling frame is the list we actually draw our sample from. For example, if the population was all shoppers, we might use a list of shoppers who signed up for coupons as our sampling frame in order to get our sample from. So if we use a sampling frame that leaves out entire groups from the population, this is the issue that we need to work around. This is called undercoverage, when we don't cover our whole population. Undercoverage obviously introduces bias. For example, if you use the phone book as a sampling frame, this would lead to undercoverage since cell phone holders would not be in the sample. And this is a very, very large group now that wouldn't be represented. The people without a landline that only have a cell phone wouldn't be represented. Okay, another issue to work around is non-response bias. If there's a systematic difference in preferences between respondents and non-respondents in a survey or poll, it is said to suffer from non-response bias. All right, so we have a sample. What do we do now? Well, we're going to use the statistic to estimate the parameter. But if we took another random sample, would the statistic from the first sample match the statistic from the second? Nope. And will the statistic from either one match the parameter exactly? Probably not. So we have this idea of sampling variability. Look at the table below. It gives results from 2 samples, each of 8,000 individuals at random from the population. Notice that the means and proportions are similar on all 7 variables, but they're not exactly the same. The income's a little bit different, 3.91 for sample 1, 3.88 for sample 2. Everything's just a little bit different. So each of these samples is a good snapshot of the population, but it still isn't the whole population. So this is what we call sampling variability. Different samples from the same population may yield different values of the sample statistic. And the goal is to minimize the difference in statistics from sample to sample and reduce the sampling error. So to reduce sampling error from a simple random sample, one good strategy is to increase the sample size. There are other strategies to reduce variability by accounting for it. One of them is to use what we call a stratified random sample. Suppose we want to make sure certain groups from the population are definitely represented in our sample, then we can use a stratified random sample. So what you do here is you separate your sampling frame into strata, groups of similar people to be represented. And then what you do is you take a separate simple random sample from each strata. Stratified random sampling ensures certain groups are represented and reduces sampling variability. This could be if you've got a poll on healthcare, you might want to make sure that you sample some people with private insurance, you might want to sample some people with Medicaid, some people with Medicare, and some people that are uninsured. So those might be 4 strata that you want to make sure that you grab people from. So here's a picture of stratified random sampling. If it helps, great. If it doesn't, just ignore it. It was my attempt at drawing a picture of this. So suppose you have a population that consists of garnet circles, green triangles, and blue squares. If I wanted to do a stratified random sample, then I would break the population up into those strata. I'd put all the blue squares into one pot, all the green triangles into another, and all the garnet circles into another. And then what I would do is I'd take a simple random sample from within each of the strata, and that would be my stratified random sample. So stratified random sampling is stratifying first and then random sampling within the strata. Now we're going to talk about random cluster sampling. Suppose that we want to be more efficient. To be more efficient, we could use random cluster sampling. In this scheme, you separate the sampling frame into clusters, and these are groups that each represent the population. So we're not separating based on making the elements in the group all similar to each other. Each of these clusters is like a little snapshot of the population. And then we randomly sample entire clusters and conduct a census in each cluster. Random cluster sampling allows efficiency, saving time and money. And if we use a combination of sampling methods, it's called multi-stage sampling. All right, so here's a picture of random cluster sampling in case it helps. Again, ignore the picture if it doesn't help. But I've got my population again of garnet circles, green triangles, and blue squares. And if I wanted to use cluster sampling, say these were city blocks or floors of a dorm, what I would do is I'd number my blocks or my floors of a dorm, and then I would maybe randomly sample 3 floors from the dorm. Here, I randomly sampled floor 2, floor 5, and floor 7. And then what happens is everybody on that floor gets into your sample. So in random cluster sampling, you're randomly selecting clusters as your sample. In stratified random sampling, you're stratifying first and then taking the random sample from inside the strata. Okay, so the valid survey. You need to know what you want to know. That's a little more difficult than it sounds. Getting your research questions written down in a succinct, clear way is a little bit more difficult, takes a little practice. You need to use the right sampling frame and avoid undercoverage. You want to avoid non-response bias, and you want to ask specific questions. This is all a little bit harder than it seems, so I would suggest getting help with your first couple surveys if you're doing a survey for research or for your job in the business world. We want to avoid sources of bias, non-response bias, voluntary response bias, when you ask a question on a radio show or just post it to an internet website and people select themselves to put in the sample. That's called voluntary response. Obviously, those are biased because the people that feel strongly and usually negatively are the ones who respond to voluntary response samples. Question wording is a big deal. Answer wording, and measurement error, inaccurate responses. So there are all sorts of ways that bias can creep into your surveys. So try to prevent sources of bias. All right, so let's say that you've done a good sampling scheme, you have your sample, and now you want to use it to say something about the population. Now we're going to talk about the sampling distribution of a statistic. You avoided sources of bias, used the best possible sampling method, wrote good questions, you reduced sampling variability, got the largest sample size possible, accounted for sources of variability, etc. So now what do? Well, now we're going to talk about how that statistic varies from sample to sample. So the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples from the same population. The sampling distribution of a statistic is described by the three features that we describe any distribution by: the shape, the center, and the variability. The central limit theorem says that the sampling distribution of a sum or percentage will become approximately normal as the sample size gets larger. This is a very important theorem in statistics that we will call a lot when we're doing our confidence intervals and hypothesis tests, because we often have an assumption that a statistic needs to have a normal distribution. All right, so that's a very important theorem, so make sure that you remember that one. All right. So now we're going to talk about how the sample mean would vary from sample to sample. For a random sample of size n from a population with mean mu and a standard deviation sigma, if the sample size is large enough, then the sampling distribution of the sample mean is approximately normal, because remember, the central limit theorem says as long as we have a large enough sample size, which lots of textbooks say about 30 is the cutoff for that, then the sampling distribution of that statistic is approximately normal. The mean of this distribution is mu, the mean of the original x's that created that sample mean. And the standard deviation of the distribution is sigma from the original x's divided by the square root of n. Now, this should make sense. Think about getting a sample of like 100 USC students and averaging their weights to get an estimate of the average weight of all USC students. If you got many, many samples and you calculated many, many sample means, you can imagine that on average, the sample mean is going to be equal to the population mean, the average weight of all USC students. So number 2 shouldn't be too much of a surprise. Now, the standard deviation of the distribution being sigma over the square root of n, I suggest that you probably also understand this one. So think about it for a minute. If we have a sample of 10 USC students and we're using their average weight of the 10 students to estimate the average weight of all USC students versus a sample of 100 students where we take their average weight and estimate the average weight of all USC students, which one would you bet would be closer to the population average more often? The one based on the sample size of 10 students or the one based on the sample size of 100? Yeah. The larger sample size is going to lead to less variability. How much less? Well, it's cut by a factor of the square root of n. So that might be a good way for you to remember the standard deviation of the sample mean. All right, now what if the sample size is not large enough for the central limit theorem to kick in? What if you don't have a sample size of 30? What if you don't get to call the central limit theorem in to get that the sample mean is normally distributed? Well, it turns out that if the sample that created the sample mean comes from a normal distribution, then the sample mean automatically has a normal distribution. So there is no sample size requirement. So if you start with a normal, you end with a normal. If you don't start with a normal, you still get that the sample mean has a normal distribution as long as the sample size is big enough due to the central limit theorem. All right, so let's do an example of an application of this. So May the 23rd, 2012, Georgia residents spent an average of $470.73 on the lottery in 2010 from this MSN.com article. Suppose the amount spent on the lottery follows a normal distribution with a standard deviation of $50. What is the probability that a randomly selected Georgian spends between $450 and $500 on the lottery? Well, if we assume that this follows a normal distribution, we can calculate probabilities associated with the normal distribution. We're assuming the average spent is $470.73, and the standard deviation of this distribution is $50. And we want to find the probability of being between 450 and 500. So 450 and 500. So we want to find this area. And we know how to find that, right? We can do p norm of 500 minus p norm of 450 and put in our mean of 470.73 and our standard deviation of 50 inside each one of those p norm statements, and R returns that there's about a 38% chance that a randomly selected Georgian spends between $450 and $500 on the lottery. That's the probability, 0.38. So now, let's find the probability that the average amount spent on the lottery for 10 Georgians is between $450 and $500. So again, we're going to draw our picture of a normal distribution. The average of 10 is going to have a normal distribution. That sample mean for 10 Georgians is going to have a normal distribution because the original data came from a normal distribution. So what's the mean of the distribution of the sample mean? It's the mean of the original distribution, 470.73. But what's the standard deviation of this distribution of the sample mean? Well, it's the original standard deviation cut by a factor of the square root of n. So divided by the square root of 10. So if we want to find the probability of being between 450 and 500 in this distribution, again, we can use our p-norm functions. But notice now, instead of just putting 50 in for the standard deviation, I put in 50 divided by the square root of 10. And we see that the probability that the average amount of 10 Georgians being between $450 and $500 is 0.873. Okay, so once you've established that the sample mean has a normal distribution, then you can standardize it because you can standardize any normal random variable. So if you take the sample mean and subtract its mean, mu, and divide it by its population standard deviation, sigma divided by the square root of n, then you have a normal 0-1 distribution, that standard normal distribution that we learned about before when we introduced the normal distribution. It's centered at 0 and has a standard deviation of 1. We use this at the heart of our confidence intervals and hypothesis tests that we're going to get to in chapters 8 and going forward from there. So that's why we point this out now. Now, another situation that we're going to have to deal with, which is most often reality, is that if you don't know mu and you're trying to estimate mu, you're also probably not going to know sigma. So what will we plug in for the best guess of the population standard deviation sigma? We'll plug in the sample standard deviation s to estimate it. And when we have x bar minus mu over s divided by the square root of n rather than a sigma sitting there, this is a student's t distribution with n minus 1 degrees of freedom. And you may remember from your last stats class, the t distribution is still a unimodal symmetric distribution centered at 0 like the standard normal distribution. It's just a little heavier in the tails, and it gets heavier in the tails as you have a smaller sample size. So it's dependent on this thing called degrees of freedom, and the degrees of freedom for this distribution are n minus 1, the sample size minus 1.